we've started talking about search problems, right? And these are these problems for which we're given an instance and we either answer yes, a solution exists, or we answer no, no solution exists. So the example we gave was satisfiability, right? Where we had to try and find an assignment to the Boolean variables such that every clause evaluated to true. And either there is a satisfying truth assignment or no assignment exists. And for the search problem to be well defined, we said that if you had a candidate solution, if you said the answer was yes and you handed me a solution, I had to have a method for checking that it was indeed a solution, like an efficient method for verifying that your claimed solution is a true solution. So SAT had this because I could just plug the variable assignments into my clauses and check that one literal is true in each clause, right? For TSP with the budget, again, I just check your tour, add up the edges, and check if they sum to a value less than or equal to B. And I was trying to show you that there's this kind of interesting line between problems that seems to be appearing, which is that some problems are easy and related versions of that problem are hard. And one example was 2-SAT versus 3-SAT. Another one I'm going to give you is traveling salesman problem versus Eulerian cycle. So, or even more related possibly is Eulerian cycle versus Hamiltonian cycle, but these are all related to one another. So the Eulerian cycle problem dates back to either 17 or 1800s. And it starts with this problem called the bridges of Königsberg. I don't know if you've seen this before, but there's a city, it was called Königsberg. I think it's called Kaliningrad now. I mean, it's in Russia, but it's sort of separate from the main part of Russia now. And there, in the city, there's several pieces of land, and they're connected by bridges. And it looks something like this. I mean, this is not a great drawing, but the bridges or the layout looks like you have some land. You have a north bank, a south bank, and then you have these kind of like two islands inside this channel of water. So like this is land here, right? This is land. This is land up here, and this is land down here. And then there's a bunch of bridges. So this is water in this area. And then the bridges are one bridge there, another bridge, right? 7 bridges in total that pass between these different points on the land. And the question that Euler asked himself was, is it possible for me to walk across each bridge exactly once? Like go on a stroll in this city and walk across each bridge exactly once? And when he was thinking about it, he basically invented or was the first person to come up with the idea of a graph to represent a problem. And so he shrunk this sort of map into a graph where basically this is one big landmass, right? And so I can kind of think of it as one vertex in a graph. And then I can think of bridges as edges connecting land masses, right? And so he shrunk this into a graph that looks like this. So that's this represents this thing on the left. Then you have another one on the right, the bank on the top, and the bank on the bottom. And what's kind of unique about this graph is that it's actually called a multi-graph because it's going to have multiple edges between the same two vertices, right? Like right here, I have two edges going between these two pieces of land. So the graph he drew then has two edges going from, right, that's these two edges here. It has these two, so it's got two edges here. It has this one edge going across. So that's this edge here. And then one edge there and one edge there. And the question, as I said, is, does there exist a path that crosses each bridge exactly once? And there's kind of two variants of this problem, or there's two ways you can think to solve this problem or pose it. One is that I have to find a closed tour, right? Start and end at the same location. And the other is that I could start and end at different points. So the characterization of the solution actually solves both of these at the same time, like this, the open walk versus the closed tour. And you can kind of picture, right? I think you might be able to convince yourself that it doesn't seem like you can do it on this graph, right? Like, because you always get stuck going back to the same landmass somehow. So like, let's say I go across up to the top, I go down. I can't go down because now or I guess I could, right? And then I go up, but I've got one that I missed, which was right here. And you can try and do different tours, right? That see if you can get through all of them, but you're going to get stuck in some way in a similar fashion. And the thing that you notice, if you think about it a little bit more, is that what you need for a vertex, suppose it's a closed tour for a second that you're going to find. You need to, every time you go into a vertex, you have to leave it, right, in your walk. And so that means that the number of edges that go into a vertex should be even. So that every time you go in, you go out on a new one. And if you look at the vertices in this graph, actually every single one is odd. If you were computing a path instead of a tour, then the one that you start at and the one that you end at can have an odd number, because you're eventually not going to leave it. But all the intermediate ones should have an even number. And this is exactly the solution to this problem. So, like I said, the path can be open or closed. That is, it's a tour or it's a path with a different start or finish. And the solution is that there exists a path if and only if, and then this handles the open and closed case. So every vertex, with the possible exception of two vertices, the start and the end, have even degree. So for a tour to exist, every vertex has to have even degree. For an open path to exist, every vertex except for two have to have even degree. That's what that's saying. So all even for a tour and all but two are even for a path. And the other thing is the graph has to be connected, because otherwise, there's no way to do it. And it's possible to satisfy the first with a graph that's not connected, right? Like just think of four vertices where I have edges going like back and forth on each pair, right? But I can't cross between the pairs, so I can't walk across every bridge. So this was kind of cool, right? I mean, it's sort of the origin of graph theory, which is neat. It's also a problem where now I'm trying to find a tour of vertices or of edges, and it seems like I have a nice characterization. So if it's even, if all of them are even, or all but two are even, then I have a solution. And I can actually compute the solution in a nice way. So the first algorithm, I call it algorithm because it predates computers, for solving this problem was proposed by Fleury. And let me give you that algorithm, but I guess I left this out. We already talked about it. So is bridges of Königsberg solvable? Based on this, we know that it is not, right? Because if we go back, the degree of a vertex, right, is the number of edges incident to it. So this has degree 3, 3, 5, 3. They all have odd degree. So it is not solvable. No, all vertices have odd degree. I think it was 3, 3, 5, 3 were the 4 vertices as we wrote it out. Yeah. No, you'd either need 2 even and 2 odd or all even. Yeah. Yeah. I guess if a vertex has a, maybe the assumption is that you don't consider any vertices with no edges incident to them. That's a good point, though. If you had an isolated vertex that actually has no bridge going to it at all, right, then it's sort of, that graph would be disconnected. But I think they wouldn't consider that to be the input graph, right? They'd just remove that vertex. The case that I was trying to eliminate, right, was just this one with connected, where you have like that. All the vertices have even degree, but there's no tour or path that crosses all 4 bridges. And so, yeah, this first algorithm, which came, I forget exactly when bridges of Königsberg was proposed, but it was proposed and this solution was provided. But then there was this question, right? Like, how do I actually compute it? And so that was proposed by Fleury first in 1883. And the algorithm's kind of nice. Like, it's not the most efficient algorithm, but I like it just because it's very simple to describe. It says, start at any vertex, or one with odd degree, it should say, odd degree, if one exists, right? Because we know if there's an odd degree vertex, then that has to be the start or the end of the path. And then go across an edge whose deletion does not disconnect the graph unless you have no choice, like unless deleting any edge after I go across it will disconnect the graph. And then repeat. Delete the traversed edge and repeat. And if there exists a path, this will find one. And so this is called the Eulerian path problem, and it can be solved efficiently. Any other questions just about the problem or its formulation, or even how this Fleury's algorithm works? I mean, I think this type of algorithm, right? I mean, he didn't call it an algorithm at the time, but it's not the way you would want to program something, probably, right? Because this predates programming. It's just something that, like, if you're thinking about walking yourself, maybe it makes sense, right? You're keeping a map, you look at the edges or the bridges that you've crossed, and you just check, like, when I go across this one, is it going to cut my graph into 2 pieces? If yes, and I have another choice, take the other choice instead, right? If I have no choice, then sure, go across that one, delete the edge and continue. And then at the end, I have no edges left to cross, and I've either found a tour or there's an edge remaining in which case no tour exists. That's the idea. Now, a related problem, and also very related to TSP, is called the Hamiltonian path problem or Hamiltonian cycle problem. And again, we have these variants, path or cycle, depending on whether we want to find a closed tour or one that goes from a start to an end. But the Hamiltonian cycle problem is I'm given an undirected graph, not necessarily complete. So there's some edges missing, between some pairs of vertices. Find a tour that visits each vertex exactly once, or determine that no such tour exists. And then Hamiltonian path problem is just like Hamiltonian cycle, but where you're trying to find something that's not closed. So an input to Hamiltonian cycle might be something like this. I'm just going to make one up. And then I ask, is there a tour in this graph that visits each vertex exactly once? I think there is, right? Again, I'm not, the way I draw these, it's going around the outside again. That actually, this one has a solution. And this problem is hard. So if given a graph, you want to tour every edge, that problem can be efficiently solved. If instead you want to tour every vertex, right, you might not cross some edges. You can see in that solution, I didn't cross an edge. That problem is hard. As far as we know. Yeah. Yeah, but you'll visit some vertices more than once. Yeah, that's where the constraint exactly once is what makes this a challenge. Yeah. We're going to talk. I'm not being precise yet. Yeah. Yeah. So the question was like, is this NP hard or whatever? But we haven't really talked about these complexity classes. We're going to get to that very soon. It's just no one knows of an efficient way to solve this problem. Now, Hamiltonian or Hamilton, I guess, was the person that sort of formalized this problem, but the idea has existed from far earlier. And so there was a scholar named Rudrata from the 9th century AD who proposed basically the same problem, but just specialized to chess, where you have a chessboard, right? It's 8 by 8 grid. And you have the piece, which is the knight, right? Which moves like up 2 and over 1, or over 2 and up 1, right? In that kind of L shape. And the question was, is there a way to make knight moves such that you visit every square on the board exactly once? Now, you never come back to yourself until you've toured the entire board. So can you find a knight's tour on a chessboard? Turns out the answer is yes. In this specific instance, this problem can be solved. And people have gone so far as to enumerate every possible tour. And so it turns out that there's this number of different directed tours, knight's tours on a chessboard, which I have no, I don't even know why people computed this, but they have. That's. Okay, let me give you one more, because we've talked about linear programming. And in our course characterization of problems being easy or hard, linear programming is easy, right? We have an efficient algorithm for it, which was, technically speaking, it's interior point methods. That's the one that guarantees polynomial runtime. But even simplex algorithm in practice is kind of like an efficient solution, although in the worst case, it's actually not. But anyway, but let me give you a variant, which is called integer linear programming. And we'll actually introduce a simpler version, which is called 0-1 equations. Problem sounds kind of abstract, but it models a lot of things. So in 0-1 equations, you're given a matrix A, where each entry in the matrix is a 0 or a 1. And your goal is to find a vector x such that AX equals a vector of 1s. So this 1 with a bar on top is just a big vector of 1s of the appropriate dimension. So I can give you just a quick example. Let's make, I'm just going to cook it, make it up on the fly. So 1, 1, 0, 0, 1, 0. So that was my A matrix. There's 2 x's now to make, 3 x's, sorry, to make the dimensions match. And then 2 numbers on the right-hand side, which both are 1, right? And we ask, does there exist a solution? An assignment of 0, 1 to each x. So each x is also binary, basically 0 or 1. And can I assign 0, 1 to x, 1, 2, 3 such that these equations are satisfied? I think the answer is yes, right? I can just, no, I think actually the answer is no in this case, isn't it? No, sorry. Set x2 to 1, x1 to 0, x3 to 0. Right, x1 equals 0, x2 equals 1, x3 equals 0. Then I'll get 0 plus 1, which is 1, and here I just get 1, which is 1. And so you can see this is in the form of a decision problem, right? Either find an x or determine that no such x exists. If you answer yes, this is a well-defined search problem because given that solution, you can easily verify it, right? You just plug it in here and do the multiplication and addition, right? The dot product basically between this vector and this vector and check that it's 1. That can be done in polynomial time. And this is a special case of integer linear programming. And so integer linear programming looks just like linear programming, but where rather than having the constraint that x is greater than or equal to 0, I now say x has to be integer. Like each entry in my decision vector x has to be an integer. So maximize C transpose x, exact same, subject to the constraint that ax is less than or equal to b, exact same. And this is the new part, right? Which is x is a vector of non-negative integers. So this is instead of just saying x is greater than or equal to 0, and it's real, right? In linear programming. So integer linear programming is very powerful. You can express many natural problems in integer linear programming. One example I'll give you is knapsack. I think someone, I don't know if they're here today, but someone mentioned back when we were talking about knapsack, something like, could I write it as a, I don't even know if they were actually saying it exactly like this, but they were basically describing a way you could write it as an optimization problem that looks like an integer program. But let's think about how we could encode knapsack as an integer program, just to give you an idea. So remember, let's look at knapsack without repetition. So you can only take one of each item, at most one. So you have n items. Each item has, like item I has a weight, Wi, and has a Vi. And you have a knapsack capacity, which is capital W. And it's without repetition, so you can choose at most one of each item. And your objective is to pack your backpack with items that whose total weight is less than or equal to W and that have maximum value, right? The sum of their values is maximal. So does anyone have an idea how I could encode this as an integer program? What could x, my vector of x's, represent? If you've never seen this before, it might be weird, but I don't know. Yeah. Yeah, whether you so what was said was whether you have a thing in the knapsack or not, right? So maybe let's say xi corresponds to item I, right? And then we might do, like, how would you then encode yes or no whether I have it? Yeah, 1 is have it, 0 don't. That's exactly right. So it's a binary, like it's a decision variable, we'd call it, right? It takes on the value of 1 if you include an item I in your solution, and it takes on value 0 if you don't. So let xi equal 1 if we choose item I, 0 if we don't. And then our problem can just be written as maximize. How do I now write the objective of maximize my value? Or don't worry about maximize. Given a selection, how do I write the value of that selection? Right, I've picked some items. In picking them, I've set the xi's to 1, right? All the other xi's are 0. How do I write out the value of that choice? Yeah. Yeah. And I'll just write it in like scalarized form, but you could exactly think of that, like kind of like a dot product, right, between the two. I'll just write it like this, just to the sum from I equals 1 to n of the value of item I times the decision variable xi. Right, so I sum up all the values for which xi is 1, like all the ones I chose. Let me write that xi a little. And then my constraints are that the sum of the weights of the items that I chose have to be less than or equal to capital W. That's just writing the exact same way. So sum from I equals 1 to n of the weight of I times xi has to be less than or equal to my capital W. And each xi has to be either a 0 or a 1. So I'm writing xi is in 0 or 1. Right? And so, I mean, I can then just, if I want to write it, define my C, A, and B, it's actually quite easy. My C is just the vector of values. V1 through Vn. My B is just my weight capacity. My matrix A has only one row in it, right? Which just has all the weights, W1 through Wn. And then Then we get maximize C transpose X subject to AX is less than or equal to B, and X I equals 0 or 1 for each I equals 1, 2, up to N. And so just like there are linear programming solvers, there are also integer linear programming solvers. Here, integer linear programming is a hard problem. You should probably already guess that because I told you knapsack was a hard problem. And if we had an integer programming solver, we could solve knapsack, right? If we had a fast one or efficient one. But since it's powerful, like for modeling, you can model decisions by just introducing these binary variables. You can model a bunch of different things. They're very commonly used. And so there's kind of two main players in the commercial integer programming solver world. One is IBM, which has a product called Cplex. And the other is there's a solver called Gurobi. And so both of these, they're free for academic use, but the licenses are quite expensive. And like if you look at most places would use these for something. Like I'm sure if you look like or Google or Facebook or whatever, they're all using in some portion of their business somewhere, they're using an integer programming solver. Like not like to load your web page or something, but like somewhere internally, right? Like they'd be leveraging this. And just like as a bit of history, the way I understand it worked. So Gurobi is the first two letters of three people's names. So it's GU and then RO and then BI. BI is for Bixby, I know, but I can't remember who the other two people, what their names are. But they're the founders of Cplex, those three people. Then Cplex got acquired by IBM, like some time ago, 15 years ago, maybe 20 or something. I think they didn't enjoy working there, or I don't know. They left, and then they formed a competing integer programming solver, which they called Gurobi. So there's two out there that are both by the same, like originally by the same people, but now they're like in competition, essentially. They must have had good, not signed a non-compete clause or something. I don't know how it worked. Anyway, so if we just compare this to linear programming, as I kind of already mentioned, we just drop the constraints that each xi is integer. So now we get something that looks like x is greater than or equal to 0. And we have this interesting line separating problems that linear programming can be solved efficiently, but integer linear programming is hard, as far as we know. And even 0-1 equations is hard. Zero-one equations actually looks quite a bit like SAT in some ways. You're making these assignments of 0 or 1 so that each equation evaluates to 1. Kind of like each clause evaluates to true, you know? Not exactly the same, but they have a lot of similarities, but as we see, the fact that two problems are similar doesn't mean that they're both hard, right? Like that's not a good proof of hardness. You might then claim that Eulerian path is hard because Hamiltonian cycle is hard or something, right? So anyway, this is kind of I guess maybe the last thing I'll mention is, so integer linear programming, right? As I wrote it here, sorry, it's an optimization problem, maximize something, right? So that's not a search problem, because if I claim here's the optimal vector of x's, how do you verify it? You basically have to solve it yourself and check, which as far as we know, there's no polynomial time algorithm to do that. So if I want to make the search version of an optimization problem, typically the way you do it is you introduce a budget and you say, does there exist a solution that achieves a value? If it's maximization, then like achieves a value greater than or equal to your budget, or determine no such solution exists. And then that can be verified, right? Because if you claim you found an x, I can just plug it into the objective, check the value, and I can plug it into the constraints and check that it satisfies the constraints. So that's exactly what I'm just going to quickly write here, which is what is the decision version of integer linear programming? Instead, I'll say, given a goal, because it doesn't really make sense to say you're given a budget and then your goal is to exceed your budget. So given a goal G, find X such that C transpose X is greater than or equal to G, AX is less than or equal to B, and X is a vector, of non-negative integers. And then if you look, right, I can basically, this just looks like another constraint. And so I can really like just pull it into here, right? Multiply left and right-hand side by -1, so I get a less than or equal to. And I can write it as minus C transpose X is less than or equal to minus G. And then I can define basically A bar, which has C transpose as the first row and then has A, and define B bar, which has negative G as the first entry and then has the vector B below it. Then the problem is just solve A bar X less than or equal to B bar X is integer. Which starts to look a lot like 0-1 equations, right? I mean, it's got an inequality instead of equality, and X can be integer instead of just 0-1, and B now is not just a vector of ones, but it's like, I think it's getting closer, right? We don't have an objective anymore. It's just find an X that satisfies some constraints. Yeah. Oh, sorry, yeah, should be a negative there, right? Yeah. Negative C transpose, yeah. Thank you, yeah. Okay, so that's a review, I guess, of some problems, some of which are easy, some of which are hard. Let's take a break, and then when we come back, we can actually talk about the classes P and NP. We've kind of been building up this bank of problems that have some similarities, but are on different sides of our hard, easy scale. And so if we have search problems, right now I'm only talking about search problems, we can have this classification of hard, which are going to be the ones that are NP complete once we define that notion. And then we have the ones that are easy, which are problems that are in P. Another complexity class I haven't yet defined, but I will soon. And so we had, for example, 3-sat is going to turn out to be a hard problem, but 2-sat, where each clause has just 2 variables, is easy. These ones you might not agree are similar, but I'll show you kind of at some later point why they're kind of similar. TSP is hard, but minimum spanning tree is easy. I don't know, maybe you think they're similar, maybe not, right? One's find the shortest tour, the other's find the shortest tree. They both have to visit all the vertices in the graph, right? Another one we didn't really talk about, but longest path in a graph in general is hard. Shortest path is easy. Integer linear programming is hard. Linear programming is easy. Hamiltonian path. Path is hard. Eulerian path is easy. And goes on and on and on. And each problem here is a search version of the problem. When we're talking about these complexity classes, we're only considering search problems right now. There's no, you can't group an optimization problem in here. So shortest path would have to be, does there exist a path of length less than or equal to something from one node to another? Now, we can define NP. So NP is the class of all well-defined search problems. So remember, search problem, yes, no answer. Well-defined means I can verify the solution is indeed a solution in polynomial time. P is the class of all search problems that can be solved in polynomial time. For a problem to be in P, it's got to be well-defined. If it's not well-defined, then you don't really have a hope of being able to solve it in polynomial time, but this is the way it's typically written. It's the class of all search problems that can be solved in polynomial time. So these are the easy ones, right? These are the well-defined ones. So first thing to notice, right? And the terminology could lead you astray is you might think P means polynomial, NP means not polynomial. Wrong, right? That's not at all what it's saying. Don't go down that. And if a problem's in P, it's also in NP. Like all the easy problems are in NP as well. NP is just the big set. It has everything that's well-defined, kind of. P is the set of those ones that we can solve efficiently. The terminology P and NP comes from, this is like polynomial time, and then this refers to non-deterministic polynomial time. When you talk about like the sort of the more rigorous model of computation is to introduce a Turing machine and talk about a deterministic Turing machine and a non-deterministic Turing machine. And then NP is the class of all problems that can be solved in polynomial time on a non-deterministic Turing machine. We're not going to go into that much detail in like computational theory because this is an ECE class and we're in week 10. But these are precise enough definitions for this, right? But I just want to clarify that point that NP does not mean not polynomial. So, and then I say this, note for a problem to be in P, it must be well-defined. So P is a subset of NP. And then the famous question is, does P equal NP? So what is that question asking you? Yeah. Yes. And maybe more like descriptive or like in terms of the problems, what would it tell you about the problems? Yeah. Exactly. Yeah. If P equals NP, then all well-defined search problems can be solved in polynomial time. Meaning, go back up to this. I haven't said what NP complete is yet, but all those hard problems are in NP. Right? Those are all well-defined search problems. So that would mean if P equals NP, that would actually mean these are not hard. They can all be solved efficiently. Definitely these ones are in P. We already have algorithms for them, right? A proof that something's in P is just develop an efficient algorithm and prove it's optimal. Then you've shown it's in P. So So this is asking, as we said, are all well-defined search problems solvable in polynomial time? I would say, I mean, I've written this. It's widely believed that P is not equal to NP. I think, that's basically true, although I think the fact that this problem has been open for so long and there has been no real progress on showing that P is not equal to NP makes some people raise doubts about even, is this a well-defined problem in some sense? Like, is there some fundamental issue with trying to answer this problem? And is that why people can't make progress on it? For example, like in the year 2000, there was these millennium problems that were released. And I think there were 7, maybe, I'm not sure. But one of them is this, does P equal NP problem? And they each had a bounty of $1 million. But it still stands open. If you go on arXiv, which is like a repository for research that anyone can post to there, so it's not like peer reviewed, you will find many, many proofs of P equals NP, many proofs of P not equal to NP, all incorrect, but every once in a while something comes up, right? And someone's like, I got it, or but I think anyway. So the world would kind of change if P were to equal NP in a meaningful way. Like, I mean, if there really were efficient algorithms for these problems that we thought are hard, because it would, for example, imply that things like factoring are not hard anymore, meaning cryptography is not secure, right? Like that our secure login to our banking site is not secure, public key cryptography, all this stuff, right? There would be a lot of implications. I mean, this all depends on a lot of things. Anyway, this is kind of I'm getting off onto a tangent, but just sort of, this is this kind of famous problem that you've heard of. So now to talk about NP complete, the last thing we want to talk about, which is really going to be the hardest problems in NP, right? Because NP contains easy ones, it contains all the ones that are in P, and it contains maybe some that are like sort of among the hardest ones. But what does that mean for a problem to be harder than another? To talk about that, we want to introduce the idea of a reduction. And so a reduction is a way to translate one problem into another problem. And using reductions, we can show two problems are the kind of equivalent in some ways. They're just expressed in different manners, but they can be reduced to one another. And with that, we can actually define this notion of hardest problems. So a reduction consists of two functions or two algorithms. So you're given two search problems, right? We're only thinking about search problems in this, basically this chapter. We're given two search problems, A and B, and we want to reduce from A to B. This is a directional thing. So it's important to think we're going from A to B. And the way we do it is there's two algorithms. The first one we call F, and it transforms an instance of A into an instance of B, a corresponding instance of B. And the other function is H, and it transforms a solution of the transformed instance, so the one I created of B, back into a solution of A. So F maps from on the instance space, right, from A to B, and H maps on the solution space from solutions of B back to solutions of A. So they have different like domains of their operation, but it's these two functions, right? So this is from A to B, and we have this function F, which goes from I to F of I, and we have the function H, which goes from a solution of F of I back into a solution where we take H of that solution and we get a solution of our original problem I. And so the idea would be this. Suppose I had an algorithm to solve B, and I had a reduction from A to B. Then I could use my algorithm for B to solve A. because I would map an instance of A into an instance of B, call my solver, get a solution, and then use H to map that solution that I got from B back to the solution for A. So I think a picture helps here. Let me draw out a sort of a diagram that shows how this works. So we take as input an instance, I. It goes into F, and out comes F of I, right? Which is now an instance of B. That goes into our algorithm or solver for problem B. B is a search problem, so we get two possible outputs, yes or no, right? Yes comes with a solution. So if we get the yes side, we get a solution S to F of I. Then we use H, and that maps back to a solution, a solution HS of I. The alternate is that there's no solution to the instance we made of B. So no solution to F of I. And then we declare no solution to I. And so this sort of, if I draw a box, oops, maybe I went too far. Like that box there makes, if you look at what happens in that box, it takes in an instance for I and it outputs a solution or no solution exists. So that box is now an algorithm for A. So if I have a reduction from A to B and I have an algorithm for B, I can use it to create an algorithm for A. And so if this algorithm ran in polynomial time, by the definition of the reduction, this runs in polynomial time, this F, and the H runs in polynomial time as well. And so my algorithm for A now would run in polynomial time. And so this type of reduction is called a Karp reduction, named after a scientist named Karp. There's also another type of reduction that we won't talk about, which is called a Cook reduction, where basically the main difference is that in trying to solve A, I can make multiple calls to my solver for B. Here I only make one, right? I make one mapping of instance to instance and then call it once and then get the solution. In a Cook reduction, I'm allowed to call the algorithm for A multiple times. Changes things a bit, but we won't go into it in this course. So now we can talk about what it means for a problem to be NP complete. A search problem is NP complete if it's in NP and all other problems in NP reduce to it. And so what that means, right, is if I had a solver for an NP complete problem, an efficient solver, it could solve every problem in NP. Because to be an NP complete, there has to be a reduction from every other problem in NP to this problem. And then we just showed if I have that reduction and I have the algorithm for it, I can then solve all the other problems. I mean, it might be a bit of work because I have to create F and H and implement the whole thing, right? But in theory now, I have a solver for every problem in NP if I have an efficient solver for an NP complete problem. So thus, if we discovered a polynomial time algorithm for a problem in NP complete, we would have an efficient algorithm for every problem in NP. And so the set of problems looks something like this. You have this big world of problems, NP. And no one knows what this looks like. This same circle could be, or blob could be P as well. What people most likely believe is that over here is P. And then somewhere over here is NP complete. And there may actually be problems in between that are neither P, so they're not efficient, but they're not the hardest ones in NP. But no one knows, right? This is like a gray area. This may be big, this may be small, you know, that we don't have a very good understanding of this at this point. And going along here, I'm like increasing difficulty. So if you want to prove P equals NP, all you have to do is come up with an efficient algorithm for knapsack. Right? You find an algorithm that runs in polynomial time and is guaranteed to solve knapsack, you've proven P equals NP, and you get $1 million. Or SAT, or longest path, or Hamiltonian cycle, right? I mean, there's lots. You got your choice. Search version of knapsack, I should say, right? So the one where we say, can I exceed a value of something with a knapsack of capacity at most W? So if we have a reduction from A to B, we write this like A arrow pointing to B. And then we say, and I feel like sometimes this trips people up, I don't know, we say B is at least as hard as A. I say that because if there's a reduction from A to B, that means I could use a solver for B to solve A. So that means B is at least as hard, like B would solve A. I don't yet know if A would solve B. So let's go through one example of a reduction, and then we'll do several more next week, but quite a few more. Yeah. Yeah, sure. Oh yeah, up here, this guy. Yeah. Mm-hmm. Yeah.
But if we also know somehow that is polynomial time, wouldn't that also imply that there's no other way?
So I think the question is like, suppose that the A problem could be efficiently solved. Is that right? And now that I've done this reduction, does that imply that this B problem can be efficiently solved? No, because what it shows is like that, think about the algorithm for B, like let's say B is hard, right? So the algorithm for B is like some super powerful algorithm that can solve a very general class of problems. A, if it's easy, is sort of like a more specific problem. And so all you're saying is like, with my super powerful tool, I can solve this simple problem. Kind of like with my integer programming solver, I can solve minimum spanning tree. That doesn't say that integer programming is hard. It just says, okay, you're using way too powerful tool to solve minimum spanning tree. You could just use a greedy algorithm kind of thing. Does that make sense as like a, okay.
It's just way too specific, I guess.
Yeah. Okay, let's see if we can go through one reduction, or at least most of it, to kind of give an illustration of how you construct these. Reductions can go from being really simple, like this first one I'm going to show you, to super complicated. And I will kind of try and give you an example of that next week, of a complicated one as well. But let's start off with a simple one, where we want to go between Hamiltonian ST path. So path, I want to find a path that visits every vertex in the graph exactly once, starts at S and ends at T. And the other problem I have is Hamiltonian cycle, where instead, that's the one we talked about, right? Find a closed cycle in the graph. So Hamiltonian cycle, given an undirected graph, is there a cycle that passes through each vertex exactly once? Hamiltonian ST path, given an undirected graph and vertices S and T, is there a path from S to T that passes through each vertex exactly once? And so I'm going to do a reduction from ST path to cycle, which means I'm going to take in an instance of ST path. I need to convert it to an instance of Hamiltonian cycle, solve Hamiltonian cycle, and then convert the solution of Hamiltonian cycle back into a solution to ST path. Right? That's the workflow. So I need to map an instance of Hamiltonian path, which I'm just calling HP here, into an instance of Hamiltonian cycle. So Hamiltonian cycle won't take in the S and the T anymore. So I'm given the instance where I have a start and a finish. Any ideas on how I could convert it to an instance of Hamiltonian cycle, where when I find the Hamiltonian cycle, I can then extract the path from S to T? I'll give you a bad idea. This one doesn't work. What if I take in my Hamiltonian ST instance, right? And I just add an edge from S to T. Now I compute the Hamiltonian cycle. I hope in the Hamiltonian cycle solution that S and T appear next to one another. And then if they do, I just delete that edge from my solution, and then that gives me an ST path. If they don't land next to one another, I'm out of luck. I don't know what I do. My reduction didn't work. That's what I'm saying, it's a bad idea. Can anyone improve on my idea? Yeah. Mm-hmm. Yeah. But that one might not visit everything, right? Like what if the cycle looks like S, T, like that? Right now I have to ensure that S and T are near one another kind of in my Hamiltonian cycle solution that I get. Yeah.
Sorry, why wouldn't that work?
Well, this is a solution to Hamiltonian cycle, and now how do I extract the Hamiltonian path from that?
What do you want to follow?
My idea is going to be this. I'm going to add one more vertex. Let's call it X. And I connect it only to S and T. And now I compute a Hamiltonian cycle on that. If it found a Hamiltonian cycle, it visited X, right? If it visited X, it had to come from S and go to T, because those are the only two edges connecting to it. So now if I delete X and the two edges connecting to X in the solution, I should get an ST path that visits everything. The other version is I then also have to argue if it can't find a Hamiltonian cycle, then there couldn't exist an ST path, right? That would be the way to argue that the reduction's correct. Let me write it out first, just this idea. So let G prime be as follows. So we have V prime, the edges in, or the vertices in V plus one extra that I'm going to call X. And E prime are going to be the vertices in my input graph, and then I add, or sorry, edges in my input graph, and then I add two more, the one from S to T and the one between T, sorry, not S and T, S and X. And then the one from X to T. This is an undirected graph, so those are undirected edges. So for example, if my input looks like this is S, this is T, and this is G, then I add in one more vertex X and these two blue edges. And now my idea is I solve Hamiltonian cycle on red plus blue. So it's, as always in my examples, it goes around the outside. And then I delete the two blue edges in the vertex, and what's left is a path that goes from S to T, or T to S. And so that then is my reduction. Let me just draw it in that diagram kind of manner. So I get an instance G equals VE, an S, and a T. My function F is going to be, oops, add X and SX and XT. That gives me G prime. This is my Hamiltonian cycle solver. If it finds a solution, which is a cycle, then I delete SX and XT. That's going to be my function H. And I output my solution path. And if it doesn't find a solution, then I just say no solution. So this is my F, this is my H, and that's my solver for Hamiltonian path. So I then should also convince you that this is correct, right? And basically, to convince you it's correct, I just have to verify that what comes out on both those arrows on the right-hand side is correct. right? That if I find a solution to the Hamiltonian cycle, then what I output up on the top arrow is a solution to Hamiltonian path. And if it doesn't find a solution to Hamiltonian cycle, then there couldn't be one for Hamiltonian path. And so that's the next step. I think we're out of time, so maybe we'll do that on Tuesday. We'll go through the proof of, it's a simple argument in this case, but this is the general thing we're gonna follow through. And sorry, and then the last thing we need to verify is that F and H run in polynomial time, right? Which in this case is pretty obvious. Okay, that's all. Thanks, everyone.